Schrödinger's cat, an experiment in quantum mechanics.
Good evening, esteemed guests and curious minds. I am Erwin Schrödinger, and tonight we delve into the peculiar world of quantum mechanics. You may know me from my thought experiment, Schrödinger's cat, a feline in a box both alive and dead until observed. Quite the paradox, isn't it? Ladies and gentlemen, allow me to present a paradox that has puzzled many minds. It involves a simple box and a cat. Imagine we have a sealed box containing a cat, a vial of poison, a radioactive atom, and a Geiger counter. If the Geiger counter detects radiation from the atom, it will trigger the release of the poison, leading to the demise of the cat. However, if no radiation is detected, the cat remains alive.
But wouldn't we know if the cat is alive or dead without opening the box?
Ah, that's where the paradox lies. According to quantum mechanics, before we open the box and observe the cat, it exists in a superposition of states, both alive and dead simultaneously. It's only when we make an observation that the cat's state collapses into one of the possibilities.
So, until we open the box, the cat is both alive and dead at the same time.
Exactly. This illustrates the concept of superposition, where quantum particles can exist in multiple states until they are observed. It's a mind-bending idea, but it's at the heart of quantum mechanics.
But how does the act of observation change the outcome?
That's another fascinating aspect of quantum mechanics. When we observe the system, our act of measurement interacts with it, causing the wave function to collapse into a single state. In this case, observing the cat forces it to be either alive or dead, not both. This equation represents the principle of superposition in quantum mechanics. Psi represents the quantum state in superposition. Ket A and Ket B represent two orthogonal independent quantum states. Alpha and beta are complex numbers, representing probability amplitudes. These coefficients determine the likelihood of finding the system in the corresponding state upon measurement. When we talk about alpha and beta, these are what we call the probability amplitudes. They tell us the likelihood of finding our system in a particular state when we observe it. Here, for instance, if alpha is 0.8, it means that there's an 80% chance of finding our system in state A. Similarly, if beta is 0.6, there's a 60% chance of finding it in state B.
Attica